In this video, we shall be dealing with the parallel combination of two cells having different EMF and internal resistances. Now, we have already discussed about the parallel combination in the case of in current electricity, that is, and we had discussed the cells to be having the same EMF with the same internal resistance in that case. We had also discussed about the series combination and the mixed grouping of cells over there. And from that, we had obtained the condition for maximum current. Now, in this case, we'll be just considering two cells as of now, having two different internal resistances, and they will be connected in parallel. So this is a parallel combination of two cells. Let their EMF be E1 and E2, and while the internal resistances are R1 and R2, and they are connected in parallel, while this end of the terminal is supposedly A and we have B at the other end. So there's a potential difference across AB. Now, from what we know, uh, let's suppose that the current that is flowing across this wire is I1 along that direction and I2 along this direction, and from that we'll be getting a total current I along this direction, where I obviously is equal to I1 plus I2. Now, from what we have learned about the relation of the internal resistance of the uh, terminal potential difference as well as the EMF, we know that if VAB is the potential difference across the terminals A and B, then what we have is E, that is the EMF provided along the respective wires. They will be related to the terminal potential difference across A and B as follows. That is, for the top wire, we have VAB to be equal to E minus I1 times of R, and for the bottom one we have a VAB, because the potential is going to be the same in parallel combination, and there we'll be having it as E minus I2R. Now, from these relations, what we can get is the value of I1 to be equal to E minus VAB over R, and also we have I2 to be equal to E minus VAB over R, not R but R1 and R2 in those cases. So because R1 and R2 are the respective internal resistance in each case. Now, if we consider the equivalent of the above case, then we have an equivalent EMF, let us say that is E, which would yield the same amount of current, and it has supposedly an internal resistance R, then it will yield the same amount of current across the points A to B, for the potential difference being VAB between those 2 points. What I mean to say is that VAB in this case is going to be equal to E minus I times of R. Now, we already know the value of I in this case. The value of I in this case will be equal to I1 plus I2. So this is E minus I1 plus I2. And as far as the resistance, internal resistance is concerned, because we had a parallel combination over there, so this net resistance in this case, the net internal resistance in this case, must be equal to R1 times of R2 over R1 plus R2 because this is a parallel combination. Now, what we wish to do is we wish to relate this, there's one more error over there, that is E1 and E2 because they are separate EMFs. So this is E1 and E2 as well. My bad. So what we wish to do is we want to obtain the value of E in terms of E1 and E2. So let's see how we can proceed with that. So we have VAB over here, we had VAB over here, we have the relation of I1 and I2. We know that I is equal to I1 plus I2. We can just substitute this value over here. Then what do we get? Well, as of now, for simplicity, I'll be using the term R instead of this big term so that it does not look that clumsy. So what we'll be doing is we'll be just putting in those values. Now E is equal to, in this case, therefore it will be equal to VAB minus I times of R. That is what we, not minus but plus, I multiplied with R. That is the internal resistance over there. Plug in those values of I1 and I2 over there for I. That means we have a VAB plus we have the values of I1 and I2 that we are going to take from here. That is equal to E1 minus VAB over entirely over R1. That is going to be I1. And then we have I2, which is equal to E2 minus VAB over R2. That multiplied with the resistance, which we have kept it like as such for the time being. Now VAB plus, this is going to be E1 times of R2, if I keep it like that, and then VAB can be taken as the common term, so this is minus VAB in each case, and we are going to take 1 over R1 plus 1 over R2 like that. And then with E1 multiplied to R2, we'll have E2 multiplied to R1, and we have the LCM terms in those things, that is R1 times of R2. So this is going to be that bracketed term and the R remaining outside. Now from this we have this value, that is VAB plus, we'll keep the first term as such, E1 R2 plus E2 R1, R1 times of R2 minus VAB. Well, this term, as you can see, is just R1 R2 times of R1 plus R2 or R2 plus R1. We can keep it anyways. And then again we can now put in these values, R1 times of R2 over R1 plus R2. Now when we multiply this term with the second term only, now with the second term what we get is, we are left with, as you can see, only minus VAB is left, because R1 plus R2 gets cancelled with the top R1 plus R2, this one, and R1 times of R2 gets cancelled with this one. So both of them cancel out and you are left with only minus VAB, and there's a plus VAB over there. So these two terms are going to cancel out, cancelling them out directly. But when this thing gets multiplied to this term over here, what I'm going to get is only the cancellation of R1 times of R2 with the denominator term in this bracket, and then I end up with something like E1 times of R2 plus E2 times of R1 over R1 plus R2. This is the equivalent EMF in case of two different EMFs connected in parallel. Now, suppose we have the EMF to be the same in each case and the internal resistance is same as well. So what we get is we are going to get the special case over here being EMF in each case is same, E1 equals E2 equals E, and we have R1 to be equal to R2 to be equal to R, let us say. So we are saying this, we are assuming this. So if we have that, then what we get is this one, the top one becomes 2 ER, and then we have 2R in the bottom, 2ER over 2R. So the R gets cancelled out, the 2's get cancelled out, we have only E. So the net EMF in case of the parallel combination of two cells having the same EMF with the along with the same internal resistance, the net EMF is going to be the same in case of parallel combination, which we have already used while discussing the parallel combination of cells previously in our current electricity playlist. So that's it from this video. We'll be discussing more about current electricity and the various special cases and problems related to that in the numerical segment. Thank you for watching. Goodbye.